Good morning.
All right. So, good morning, students, and welcome back to the NLP class. I think you guys are catching up very well, and hopefully you guys understand the first lecture. It's not so difficult, right? I guess, right? It's still manageable, right? But once you code, then you feel like, oh, so difficult, right? The first coding will be difficult, right? But once you're able to do it, you will be fine, right? So I urge you that I have to emphasize that when you study with me, you only understand 20%. You actually learn only 20%, right? But the actual skills and understanding and knowledge and wisdom comes from you coding. So you need to learn to manage your time wisely. I know you have many courses, but set aside a quiet time where you can work for 6 to 7 hours uninterrupted, right? On the assignments. Then in the beginning, it takes 10 hours. But if you fully do it by yourself, it will take next time 9 hours, next time 8 hours, next time 3 hours, right? So, but if you don't set aside a good time, you will always struggle, right? So I think the first assignment is very important. And then, so in this good time, I have to make sure that everyone enroll in my class is in the Moodle, right? So I can again make sure that you guys are all in here. So if I'm in the Moodle, all right, go to participants, right? Currently I have 32 participants, so hopefully everyone already in the system. The next thing you can quickly go is go to the course, and you can go to the assignment A1. All right, so it's posted, and you can clearly see it's open today, right? 17 January, which is today, I guess, and then it's due on Thursday. Is this midnight or 12 o'clock? Midnight or 12 o'clock? Midnight, right? Midnight, yes. And he will check every Friday morning, okay? Because Friday is the only day he is free. So he will wake up morning Friday and he will check. Anyone don't submit, he will not check. And this is the only time he will check because he's very busy too, same as me, okay? So Thursday, do it. Don't work on Thursday. I tell you already, this is assignment 1. You should start it nicely. Set aside a good time to work on it, right? At least 10 hours, I think, if you guys. But how many lines of code actually? A lot, okay. You should not say that to the students, okay? So let me explain the assignments a little bit, all right? It's not so intimidating, all right, as your TA said, right? So I already write like 60 to 70% of the code for you, all right? So you just use my code. So how do we start explaining this? You will create a search engine, all right? But it's not exactly Google, because if you crawl all the documents in the internet, it's impossible, right? So basically, you are creating something called information retrieval. And basically, if you search Harry Potter, it will give you some kind of top K documents, all right? So that is what we want, right? So for example, if you say Harry Potter, and in your folder, it has maybe 50 documents. It will retrieve the top 5 documents in about Harry Potter, maybe top 5 sentences. All right. So it doesn't matter document or sentence, it works both, right? It doesn't matter, right? So that is what we want to do. All right. And here are the instruction, and in which you can take a look, but you don't. I think for those who study my machine learning class should be fine. For those who do not, you should also be fine. Just read. I write everything very verbose, right? So that you guys understand everything. Next thing is The first instruction told you to read Word to Vec and GloVe papers. All right. So you have to. I'm not sure you can click. I'm not sure. I think the reference is down there. You read and read. All right. This is the thing. This is the learning technique I teach you. The first time you read, you should not spend like 3 hours to read. All right. Because you will feel like I don't understand anything. I never read paper before. And when you read, you don't understand anything, right? So you read a little bit and go to my code and come back to read, go back to my code, a little bit, go back and forth. Then you can quickly understand the key essence, all right? But mainly I want you to read just to get a feeling, right? What they actually do. But if you don't understand me, my lecture should be fine and my YouTube video should be fine, all right? But if you read my paper, you will know how to do the evaluation down there, right? And then I would say that train the word to vec with or without negative sampling. You don't need to worry about this. All the code is already done for you. I already made all the code. You just need to shift enter, shift enter, shift enter. That's it, all right? But of course, you need to change the data set, right? And GloVe, right, from the lab lecture. But one thing you have to change is you have to change to real world purpose, right? My example is only using a very simple example, so you need to use a real world example purpose. If you don't mind, you can follow what Gan has suggested. Just use NLTK dataset, and there's a dataset called news. You just use this one, right? But if you guys want Harry Potter, then you just load some some text file, Harry Potter. You can also do that, right? So that can also be done, all right? And here I say use a window size of 2, all right? So that everything is specified correctly. So task 1 is that, should be fine. I think this should be take around 1 hour. I think, yep, 1 hour per each. Okay, so they have with and without, right? And also virtual vec and GloVe, right? So those are a huge combination. They need the 4 combinations they need to do, right? The next thing you need to do is actually this is the only thing you need to do. Number 3 is the web application development. All right. For task 2, you have to compare skipgram negative sampling, GloVe. All right. So there are 3 models you need to compare. So I teach you already skipgram. I already teach you negative sampling, and I will also teach you today GloVe models. And you have to write in the table training loss and training time. All right. So that is not difficult if you already do task 1. And then what you want to do is you want to use the word analogy datasets. All right. To calculate, this is the typo, between syntactic and semantic accuracy. All right. So for example, syntactic is something like fly, flying, eat, eating, right? You guys, so this is mean 100% accurate, right? 100% accurate. So this is a syntactic analogy, okay? Semantic accuracy is something like, okay, Chucky and deep learning, Chuttipon, ISDM, yes, something like that, right? So this is semantic analogy, right? And you don't have to come up with this test set. The test set is already here. The data set is already here. You just download what Gan has prepared for you and just test it, okay? Just test it. How to test? Remember, I have a code. Positive, positive, negative, right? Just use that line of code, then you should be fine. Right? Yeah, there's something note, so you please read, and you will find this problem, but don't worry, we already know. And then based on that, we want you to do also similarity data set, right, to find a correlation between your models and also the provided similarity metrics, right? So that should be very simple too, right? So those are two tests that you need to, right? I would say for those who don't really know Python, PyTorch, it would take a lot of time. But again, you have to struggle, right? In the beginning, you have to, if you never took my machine learning course, then you should go study, sit with your friends, ask them, slowly do study, okay? But you cannot neglect, okay? Because this is the main skill for you to get your career, right? So if you don't do this, I don't know what kind of jobs you will do. Maybe you can do database, but yeah, I think this is very necessary skill. All right. The last thing you need to do is create a web app application, right? And this web app application is very, very simple. All right. So for example, the web app only have one box. Okay, just have one box, and you just type food. All right, you just type food, and then it will return you 10 document. All right, and who upload this document? You are the one who upload the document, right? And upload, right, the document, right? So this is a very simple one, and I don't mind. This is not a web app class, right? So you can use whatever, right? You can use a Flash, right? To do that, everything should be fine. Very, very simple, right? Django could be very heavy, too heavy for your task. So Flash should be fine, right? But again, I cannot teach you everything about web app development. If you want to do, you can come to my lab, do some internship, or maybe work with Gan. We all know how to do this in a professional way. But for this class, this is not a web application development, so I cannot teach you, beginning, you need to do this, CI/CD, do this, Azure, do this, AWS, do this. That is too much for your class, all right? So you just do Flash, right? So that should be fine for your A1. Okay. Great. Anyone has any question on your assignment one? Okay, I can see your guys' face very confident, right? Very excited. Yeah, don't worry too much. And don't be depressed. Enjoy. Enjoy. You can do a little bit. Do. If you do task one, finish, cannot do task two, then submit task one and continue to do task two. Okay? Enjoy. Don't be depressed. I created this for you to learn, not to get depressed, right? So very important. One tips for you. You don't have to worry if you cannot do it. I will ask Gan to give the solution, right? So he will give you the whole Jupyter notebook. After Friday, we make sure everyone submitted, no late work. Then he will release the solution, and then you can take a look how he do, right? So every time, if you can do task one, cannot do task two, okay, just wait for his solution, study, and next time AU2, try it again, okay? Okay, so that is the idea. Okay, great. So we spent like many, many weeks to make this, okay? Many, many weeks. Okay, great. So that is the assignment. Now we go to the course. All right, so did I record? Okay, I record. So last time we studied Word2Vec, right? And that is fantastic, right? So Word2Vec is in 2013. Today we're going to study something called GloVe, which is come 2014. All right, and Word2Vec is by Google, is by a Google guy, right? But in 2014 we have something called GloVe. It's by Manning and his team, and it's by Stanford, right? And that's why Stanford is probably one of the oldest NLP institute. But of course, don't quote me. Probably there are maybe more classic one too. All right. So that is GloVe, right? All right, so again, where are we in this class? If you're lost, like Chucky, where are we? We are here. Okay, we are in the GloVe, right? And once we finish this two, we will go a little bit here, all right? And we will go here, 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 okay? So that is the plan for our course. All right, so let's talk about the limitations of word2vec, right? And I think a lot of you already asked me some of the questions here already, right? So only look at the local words, right? So if you have window size of 2, you only look at here, right? It doesn't look at everything in the whole document, right? So it does not use co-occurrence statistics from the whole document, right? So how do we do that? So that's why GloVe actually suggests that we should use the whole document statistics, not only like window size of 2, blah blah blah, right? Word2vec still have problem with out of vocabulary, right? So for example, if I train my Word2vec with 50,000 vocabs, it's perfect, right? Now I got embeddings of 50,000 words, right? But the question is, if I use it in another document and that document have another new word that it never see, then do we have that embedding? We don't have that embedding, right? So what to do? Cannot do anything, right? So a lot of people suggest a subword embedding, right? Subword embedding. So what is subword embedding? Subword embedding is something like, okay, you have flying. So Word2vec has a embedding for this word, right? Flying, right? But later on, we will learn that this is not a good way because you will have so many unknown. So one way is split this to subword. Fly, we have one. And ing, we also have one embedding. By doing that, there's a less chance of having unknown, right? Because if we split things into subword, then most of the word comes from some roots, right? So then there's a lesser chance of hitting unknowns, right? In which we can talk about FastTech, not now, but later on, right? FastTech is by Facebook in 2015. Yep. There's also a problem that Word2vec doesn't actually capture contextual information. It doesn't change. One word only have one embedding. So I think our friend somewhere here asked me, Chucky, it doesn't solve the problem of the beginning. We learn about the word shit, right? Shit is happen, step on shit, right? Real shit is happening. They are all different meaning, right? So if you have only one embedding for one word, it doesn't work, right? It's still one word, right? So Word2vec did not fix this contextual information, right? The key is how do we have multiple embedding per word, right? That is not an easy answer, right? That is not an easy question to answer, right? So then we have to study that, right? Which we will study later on through something called ELMO. This is 2017, and BERT is on 2018, right? So you can see that when I talk about the year is very important for the learner, right? You understand, oh, this guy come first, and then I have this, and then you also understand the logic, how people think, right? So you don't need to reinvent the wheels, and you will trust that this is the best way, right? But anyway, that is the history that we're going to talk about later on. Today, we're going to focus on GloVe 2014, guys. So we can say that Word2vec is a prediction base, right? How about we have something called counting base, right? Counting. What do I mean by counting? Counting means like this. Chucky is flying on his balloon. All right. And actually Bloom is L or R? Huh? R, right? Yeah. Like that, right? Yeah, okay, good. Because Bloom is, I think that Bloom is related to education, yes. But anyway, Chucky is flying on his Bloom, right? You can count. For example, if I put a window size of 2, I can say that Chucky always stay with ease one time, and Chucky is always stay with flying one time, and Chucky never in a window size of 2, okay? 0 is 0 and Bloom 0, and of course I can do for the next one. Is Chucky, yes, is never itself. Okay, you can say 1. Okay, flying is 1, and on is 1, and west. I forgot Chucky actually. Maybe Chucky here is also 1 here, or 1 here, and his is no, and Bloom is no, right? Something like that, right? So the idea is that if we can count, if we can come up with some kind of statistic like this, then maybe we can say that, oh, Chucky is always happen together with is like let's say 50 times, right? Then probably these two guys should be similar, right? Should be similar, right? So this is the way to think, not like word to wake. Word to wake is any word near you, you are similar. Here is the whole document, okay? Whole document, you appear with who always, right? And you create this table, right? But of course, the question is, how do you actually convert this to prediction or etc., right? So that is another question, right? So there are two work that actually work on this, and the first one is co-occurrence matrix in 2005. So pretty old, right? So this idea has happened in since 2005, but then GloVe actually make that even better in 2014. So let's look at this one first. All right, so here is my definition again, right? So if I have window length of 1, just 1, and I have example corpus of I like deep learning, I like NLP, I enjoy flying, this would be the table I created. You don't have to check whether it's correct. You can go home and check, right? But this is the table I got, right? So during 2005, there's some problem that we actually met. That is this is very high dimensional, right? So if I have 10,000 words, this is probably so big, right? And probably 10,000 by 10,000, right? So this is a huge array that I don't want to maintain, right? So how do we convert this? Let's say I have 10,000 words, right? If I have 10,000 words, then I need to have a matrix of size that, right? That would be the array I need, right? Which is crazy. I don't want to spend so much money just to store this guy. And I can't imagine when I train this guy, this would take like ages, right? So how do we convert this to something like a much smaller scale, right? Like 1,000 times 1,000, for example, right? So that is something we have to think about. So here, the idea is, okay, so how do we store the most important information? How? How do we convert something called 10,000 by 10,000 into only the most important information? All right, basically convert this into this. And I think this sounds very, very similar to you. This is a dimensionality reduction problem, right? Remember? What is the algorithm we do in machine learning to do this? We learn in machine learning class. PCA, right? Exactly, PCA, right? And there's so many ways we can reduce this matrix, right? You guys will learn linear algebra, right? There's an eigendecomposition, right? And also the singular value decomposition, right? Right. Of course, you may say, Chucky, I don't remember what are they, and what are they, but they are not really difficult. They are just some kind of matrix manipulations and to choose the most important columns, right? So those are the two techniques we have in mind. So scientists is basically like that. They first think about the philosophy, then based on that philosophy, they try to realize it, and then ask the right question, how to reduce the dimensionality. Once you ask the right question, you will have the tool, right? Then what the scientists do, they quickly get an A4 sheet of paper, try, right? How many days they try? Of course, many months, 3 months, 4 months, 6 months, right? Not like I teach you one day finish. They try many, many months, right? So that's why for those who are researchers, you need to be patient, right? When you do research. But anyway, we have this idea, right? So how that looks like, and actually, if you understand SVD or eigen decomposition, that should not be difficult, right? Right. So we can say that okay, let's try something called singular value decomposition. So what the algorithm say? The algorithm say that any matrix X. So let's say this X is 10,000 by 10,000. All right. So this is the X, right? Can be actually written as U sigma VT, right? So this is what the singular matrix say, right? And so here, if this is 10,000 times 10,000, right? Then U will be 10,000 times 10,000. Sigma is also 10,000 times 10,000. Here, because our N and M is the same, so it looks so same, and V is also 10,000 times 10,000. All right, it looks a little bit weird because our M and N is the same, right? But here, what we can do is we can reduce, once we decompose into this tree, we can choose only the K columns, right? So for example, we can choose only 10,000 times 3 or 2, right? We can take the first 2 columns, right? Why only the first 2 columns? Because once you decompose A to U sigma V, the first 2 columns will always have the highest eigenvalues, right? Remember? And highest eigenvalues means that they possess the highest variance. So they basically, but the first few columns are the one that contains the most information, right? So that's why we can take the first K columns of U. We can take the first square K component of sigma, because sigma is K by K. And we can take, we don't actually need to take V, because V and U are basically quite the same thing, right? So you just take the U and sigma multiply together, you will then get the new X here, in which X, the X is simply the dimension of, if M is 10,000, and if I choose K to be 50, then this would be the new. So what does this mean? Well, it means that you have 10,000 words, each of them, how big? I have 10,000 words, each of them how big? 50. 50. So each word has a size of 50, right? Chucky, so can you tell me, how do I choose K? I cannot tell you, right? The standard in industry is 50. Some people use 100, remember? Some people use 300, right? Right? I never see people go beyond like 1,000. Right? So you can see that by using SVD, you can break down into 3 matrices and just get the K and then the K columns and K square thing, and then you multiply them together, you'll get the reduced matrix. In Python, it's super easy. You just say SVDX, you will get 3 guys. You take the K using NumPy, colon K, right? And this one is also colon K, right? Multiply together, you get the reduced matrix, right? So in Python, it's super easy. So this is the way that Rode suggested, right? Super genius. You can see this guy is 2005. We are not born. I am born. You guys are born already, but we are still like not know yet. But AI is not very famous that time, but this guy is very smart. Yep. So this is 2005. But of course, there's a lot of things he even improved it, right? So this is what you guys can read his paper if you guys have time. But no, I don't think you need to because it would take a lot of your time. But anyway, I can quickly say this is it's not really relevant for you guys. But he say that he found that raw counts are not really work because some words happen together like, oh, this is too many too. Like, let's say like that much of time, 500 times, like is and is eating. These two words like to be together, right? 50,000 times, right? And then maybe you have another one is playing. This one is 1,000 times, right? And you can see that because this guy is so big, more than this, then your embedding, your language model or whatever, basically override by this guy, even though this guy is still important, right? So raw counts is not good. So log is better, right? So if you take the log of this, I don't know, 10 to the power of what is 500,000? I don't know. I just, okay, let's say 12, okay? And then this one is 10 to the power of 3, right? So you change this number to 12 and change this number to 3. He found that is better because you don't over exaggerate like crazy like dominance by anything, right? So that is what he found, right? He also found that you should minimize, you should try to cap this number into some range. So that is what he do, right? And also anything that is so frequent, he want to minimize, he want us to ignore those words, right? So another thing you can take a look, it's not really relevant for you guys, but I just told you guys the idea in 2005. All right. Not in the assignments, not in your quiz, nothing. All right. I just tell you a fun story. All right. And yes, he actually do this experiment. He found that his results is very good. Swim and swimmer, always very related. Driver, swimmer, teacher. These are all embedding. And when he draw a vector, the vector is always the same direction, which is very interesting. All right. Now we finished the idea of a count occurrence thing. What is the thing that Manning in Stanford in 2014 actually proposed? This guy definitely learned word to vec, right? But he also read that paper, 2005. He want to combine them, right? He want to combine them into something called GloVe, and this is the formula, right? Okay, so firstly, I have this slide. So this is what Manning has probably thought of, right? And I just reiterate what he say. He think that count-based is fast training, very good for use all the statistic needed, but scale badly to frequent words. That's not what I said. For prediction based is it can capture complex patterns, but it did not use everything. He asked himself how he can use both prediction based and count based to create this ultimate embedding, okay, in 2014. And actually, he is also a genius, right? Or maybe his student is genius, right? So this is what he proposed. And I think, okay, we can talk about this slide first, right? And then I think the equation is right here, yep. Okay, so here, so his student named Pennington, a PhD student, right? They know that there's a problem with raw counts, so he quickly fixed that. He used the ratios of co-occurrence probabilities, right? So you basically you try to understand the relationships between some word and some word using another word called prop word K. All right. So for example, so K here is the prop word, solid, right? And if you want to know the relationship between ice and steam, you can take the ratio of these two words when talk about solid, right? So you can see that this true word are both related to water. You can see, right? But both of them are not really related to solid or gas, and also not. They are equally not related to fashion, right? So they are very. The ratio is very that number, right? So you can see that by capturing these ratios, you want to know the relationships between ice and steam, and you use the prop word called K to use as an anchor to understand the relationship between this sort. So this is what he proposed, and based on that, he come up with this equation, right? So this equation looks very intimidating, right? But actually, it's very simple. All right. So I'm gonna talk about this very quickly. The first thing you need to know is this. Okay, I will pause a little bit. I think this is very familiar, right? The embedding of word I, all right? And the vector or the embedding for word J, all right? So this is basically the dot product of two words, right? Right. So this could be bank, and this could be finance, right? These are the two words, right? But how do we control that it should be similar? Maybe I can have also two words like bank and cat, right? Okay, so this loss function dot product them together, right? So how do we control that they should be similar or different? Well, what do we want to do is it should follow the log of the co-occurrence between xi and j, right? That's it, right? So basically, if they are related, this one should be related. If they are not related, this one should not be related. Where do you get this? This is from the co-occurrence matrix. That's it. Only the meaning of this GloVe thing. Very simple, right? You want them to dot product, and you want them to be very similar to this guy. So you take a minus because this is a loss function, right? So you want them to be very basically the same as the co-occurrence matrix. So you basically compare them together, right? These two are not important. Just shift a little bit. So these two are not important. This is the bias for this word. Bj is the bias for word j. Not important. And there's only one term we left for this loss function, and that is this term. That is this term, right? And you may wonder, like, what are this term? And this term is basically it is a capping function for frequent items or rare occurrences, right? So if any words happens too many times, you want to cap them, right? If this true word happens 50,000 times together, this function f will convert them into 100, for example. Understand? Yeah. If this two word only happen in one time, it will be one. Okay. The function will not do anything, right? So that is basically what this function is. It's just a capping function to make sure that if it happens too many times, it will cap it into some number threshold, right? And the paper tried many numbers to make sure that they understand how to deal with this. Good. So this is the GloVe, right? A very, very elegant loss function, and it works very well. I will show you a couple of slides, and I know you guys already, oh my goodness, so many equations and thing. I will let you guys rest a little bit. So this is actually what he tries from the GloVe. He try the nearest words to the frog, and actually you can actually get a very good results, right? I'm not sure what is that, yeah, but they are all frog. All right, great. So I think that is GloVe, and let's take some break, right? And we go to the next section, which is called how do we actually systematically evaluate word vectors. Yeah, see you.
Sorry, Professor. Sorry, Professor, you forgot to unmute your microphone.
Thank you very much. Yes. Welcome back, guys, to the after the break. Yes. So you can imagine that. So I want to talk about the two questions I have. One question is, can you explain this one more time? And another question I got is the ratio, the probability ratios. I will talk about that, right? So for example, I can be bank and J can be finance, right? And let's say once I compute the co-occurrence ratio, I got that these two guys are really, really high, okay? They happens to be together. So let's say 10,000, okay? I don't know how that number comes, but they happens to be together. The ratio statistics is 10,000, okay? That means they are very, very related, right? You can already see why I need to put a log, right? The log here would change this to be 4, right? 4? 4 or 5? 5, yeah, 5. Should be 5. Yeah. Right? So if you log this one to the base of 10, it will be 5, correct? 5. Or 4 or 5, okay? 4? Okay, good. Okay, it's 4, right? Now, so basically when we define this loss function, we use this as the way to define the similarity score. This should be when if this vector bank for bank and this vector for finance, when they dot product together, they should be close to this number 4. Understood? They should be the same number, right? So we use this as a definition of similarity, and we tell that these two guys, when they dot product, they should get 4. Okay? Yes, that's it. And some people may ask me why minus, because you want this guy when minus to this guy to be 0, right? Because that is the loss, how the loss function works, right? You want him to minimize as much as possible. So automatically, you force these two guys to follow these statistics, right? So that's it, right? So it explains log, it explains minus, right? So that is this J function, right? Now, the next question I have from your friends is, how do we actually compute this? Actually, I can compute just the co-occurrence, 10,000, right? But he found that actually ratios is better. But to compute this number, xij, we can do something very neat here. So we can go back to this slide, right? How do we do this? Well, we can do something like this. We can say that the probability of solid given ice, solid and ice may be okay, related, but also not so related, right? So this is like the ratio in which they happens to be like very low, right? But still not some number. This is still positive, okay? Like 0.00001, right? So that is a very small number, right? What is the probability of solid given steam? Like how many times these two words happen together? Well, also not so much, okay? Like, but you can see ice is a little bit higher than steam, right? Yes. And then using this prop word solid, we can say that take this probability divided by this probability, we got 8.9, right? If these two words both are not related to solid, it means they are related, right? This is the meaning of this technique. So ice, not so related to solid. Steam, also not so related to solid. Then when you divide it by together, then you will get a very big number, which explains that these two numbers may be kind of related. But this is not always the same, right? You can use another prop word, gas, and you'll get a number. You get a water, you get a number. You get a fashion, you get a number. So how do we define the xi steam that we want to use in the next equation, right? Remember xij. We want xij, right? How do we get this, right? We just take k words randomly from the corpus and average them together. Average this number together, right? Then we'll have the feeling how much they are co-occurrence and how much they are related, right? So those are the idea. All right, you guys got it? I speak too fast? Who understand? Raise your hand. Okay, who don't understand? Raise your hand. Who did not listen? Yeah, basically I can choose, let's say 10 prop words or 15 prop words, whatever, randomly from my corpus, and I do something like this, okay? Do. And then I will have the relationship between ice and steam, this number, right? I will have how many numbers? If I use 10 prop words, I have 10 numbers. If I have 15 words, I have how many numbers? 15 numbers, right? High mean what? High mean they are closely related. Low mean not related, right? But using the prop word, sometimes it's high, sometimes it's low, right? So by choosing prop word like 10 or 15, you will have a very good way to measure, like, are they really related, right? In different aspects. Then how do we get a one? We only want one number, right? We have 15 numbers. How do we get one number? There's so many ways you can minimize, maximize, but I think the right approach is average them, right? Just average all these 15 numbers. You will get one number called xij, which is that number. All right. So that is take the average of these 10 numbers. Right. So that is how this paper proposed. Good. Then you may ask me, Chucky, how many K, what K they use? Again, they do some experiment. They try 5, 10. You guys read the papers, you will know, right? Great. But I'm very sure they randomly pick. They could not manually pick. That is not the right way to do prediction. Yep. Great. So now, so those are some questions I got during the break. So now we can proceed to the word vectors evaluation, right? So as a researcher, when you do research, the first question is define. Once you define, you can formulate as an equation to solve it. But once you solve it, how do you know it's good, right? That is measuring, right? So that's why I need to teach you how to evaluate something. That will be also something you will do in science, right? So in this area of word vectors, there's a two-way, intrinsic and extrinsic, right? Let me explain the one that is very easy, right? Extrinsic. Extrinsic is basically when you use that embedding on a real task, okay? like question answering, ChatGPT, whatever, summarization. These are something like the real task, right? Paraphrase generation, right? And once you use that embedding, it gets high performance, then it's good, right? Finish, right? This is called extrinsic evaluation, right? But in NLP, we can also do something called intrinsic what? Evaluation, right? So we can use analogies, right? Analogies. For example, I asked you guys, maybe I use my GloVe version 1, okay, and GloVe version 2. Okay, you tell me which version is better. Okay, my first version is Austria. Actually, I don't know. Italian, Italy, pizza, Thai, sushi. Okay, I tell the computer to, I use GloVe and use this operation, right? You may wonder, like, how do I do this? Well, what you do is you take the Italy plus Thai minus pizza. You will get this word. Understood? So you may say, how do I do this? Very simple. Italy is a vector. Thai is a vector. Pizza is a vector, right? Then once you do that operation, you will get some vector, and that vector is that returned by GloVe, right? So that is the operation we already learned, right? So let's say I have an embedding called GloVe version 1, and I got this answer sushi. Okay, I do again. I train again my embedding. I do Italy, pizza, and Thai, and what is the most famous food in Thai? Huh? Huh? Tom yum, yeah, tom yum. Tom yum, yeah, tom yum. All right, then you tell me which one is better. Of course, it's version 2. This is an example of intrinsic evaluation. It's not related to any task, but you try to believe that if this is a good embedding, it should be able to do this analogy very good, right? So that is like one. So this, by the way, this is called semantic accuracy, right? But of course, you can also do syntactic flying, eating, something like that. So this is called semantic accuracy. Okay. Yeah, so that is the typical way we evaluate word vectors, especially in this paper. Anyone has any question? This is exactly what you will do, right? Exactly your assignments will ask you to do. Right, so I have this slide, right? I already talked about this. A is to B, C is to what? Semantic could be A10 is to Greece, as Berlin is to A10 is to Greece, as Berlin is to Germany, right, guys? Yeah, Germany. Yeah, you guys wrote embedding is not good. Syntactic is something like this. Dan is to dancing, as fly is to flying, right? Yeah. You guys, human can do very well. If we train the embedding should do both correctly. Yep. And then you may now ask me, how do I code this in my assignment, right? So this is exactly the equation that you need to do, right? So you take, if you have A to B is to C to what, right? What do? You take the embedding of B, take away the A plus C, dot with any embedding in which this I can minimize the distance. All right, you choose any word that can, when dot product with this whole thing, minimize the distance, right? So that is like the like the formal equation. And the bottom term is simply make it into unit vectors. All right, so this is the magnitude, which basically minimize the distance. If you don't understand this, don't worry, it's all in my code, right? Everything here is all in my code. I already do 60 to 70% of my work. So you guys, you just do the rest 30%, you are 70%, right? Great. Anyone has any question to this formula? Okay, okay, great. Okay, great. So I'm not going to talk about all this experiment that this paper do, but I just want to showcase like how people, when people say it's good, they don't just say good, right? You guys will do thesis. Some of you will do research study. You want to propose some embedding. You want to propose some model. When you want to propose something better, you need to make a table like this, right? You don't need to compare so crazily, but at least they compare so many versions, right? Like GloVe with whatever we don't even know, right? They also compare with the SVD version, right? That we already learned, right? And they found that semantic, theirs is best. Synthetic, GloVe cannot win CBOW sometimes, right? But if GloVe is 300 size of 300, it's always win all, right? You can see right here. I'm drawing for the online students. You can see they always win when the size is 300, right? GloVe. And 42 billion. You may wonder what is this size, right? This size is basically how many words they train. Okay, how many words they train. So if they train only 1.5 billion words, it's still not so good. 6 billion words, okay. But if they really want to be really good performance, 42 billion words, right? In that corpus, then you will get a very, very high performance. Right? And I'm not going to talk about, and this could be the example of the 42 tokens they talk about, right? If I'm not wrong, common crawl is basically they crawl from the whole internet. Everything in the whole internet is common crawl. I don't remember gigawords. If I'm not wrong, gigawords is from CNN and daily. What do they call in the US? Daily news, something. CNN, daily news, those are BBC, those kind of thing. And Wikipedia is the Wikipedia. Okay. So those are the data sets they created. Okay? So these are the things they do in this paper. Fantastic. Okay, any other column I did not teach you? No, I don't think so, right? I think you understand all the column. Of course, you don't know what is IV, LBL, what is HPCA. I don't too, okay? Because it's just too much. At least I think we all know I think we know S and CBOW and GloVe, right? And I think we know S and L. S is like probably something variant, like logarithm, something like that. But no, we don't know this. We don't know this. But it's okay, right? We okay. As long as we know some, it's okay. Okay, great. So those, I think we understand this table very well. So here they are basically measuring the vector dimension, right? How the vector dimension affects semantic syntactic accuracy. They actually compares whether the window size, how big the window size is good, right? And you can see the bigger window size is better, right? And there's also asymmetric context, right? Asymmetric context means that the window size asymmetric means that if this is the word, you only take the future word, okay? When you do co-occurrence, you want to say this word happens to be together with that word, right? Symmetric means two side, two tail, right? But asymmetric means only one side, okay? And they found that when you do for that, it happens to maybe what is the insights here? The insights here is probably Semantic is better right here. But semantic is always better, right? Yeah. So I don't know the insights very well, but I think that the trend is still the same, right? Once you increase the window size, it's still green, orange, right? Green, orange, yep. So I guess that is something we can grasp on this. This guy just tried to do all the experiments he can to understand everything. So you guys don't, I know you guys all have this question, right? So when you have this question, you do experiment, you will know the answer. Of course, he also compared with the training time, and I'm not going to talk too much, but the story is that they try to say that GloVe takes much lesser time. Like you can see, it only takes, the GloVe is the orange line, right? It only takes like 10 iterations to already win the skip graph, right? This is what they are trying to say. And again, they only take like 5 iterations for GloVe to win CBOW in this space for this CBOW, and that is skip graph. So that is the story they want to tell when they publish the papers. Pretty cool. Exactly. This is exactly another thing you will do in your assignments, right? So firstly, tiger and cat, are they similar? Yeah. Tiger and tiger, 10. Full mark, right? Book and paper, yeah. Stock and phone, no, right? You can see it's low. So this data set is called word sim. It's made by human being. It's made by human being. Okay? This data set is made by human being. So I want to know, okay, if I have this data set, then I also have GloVe, right? Or I have also word embedding. So let's say I have tiger 2, 3, 4. I have cat -109. I dot product, I will get a number, right? When I dot product, I will get a number, right? And I do for all this. Then I will have another column, which I dot product myself, right? I will have a lot of numbers, right? What the paper say is that if these two columns are highly correlated, is good or bad? It's good, right? It's good. It means that your embedding actually resemble human being, right? Because when you dot product two vectors that you already trained, it's very close to what the human keep the score, right? So if there's a trend of direction, then is very good. And this is, you may think this is difficult. It's just a Pearson correlation, like just one line code, right? Pearson correlation, you get a number from 0 to 100, and you'd say that you can see that GloVe is super like correlated to human being. Okay. Anyone has any question on this? I see a little bit confused face. Who's monitor? Anyone has any question? Which part? So this one is basically human defined, and based on what human defined, we can take the embeddings trained from the GloVe of each word. We dot product, we get one number, right? We get many number, right? We take the tiger dot product, we get one number. We get book, we do book paper, one number, right? Then we do Pearson correlation, right? Pearson correlation. If they are correlated, they will have high number. If they are not correlated, they will be low number, right? By the way, when I do correlation for 2 columns, how many numbers I will get? One number, just one number. Just one number between 0 to 100, right? How much they are correlated, these 2 columns. Do you guys remember correlation? How do we do correlation? Yeah, basically like covariance, right? Like covariance. So if you don't remember how do we do correlation, the mathematics, you go home and just study 1 minute, you will know. Or at ChatGPT, you have the formula. All right, so that is that. So that is something very nice experiment they did. Here they now come to the example of doing extrinsic evaluation, right? And they do something called name entity recognition, right? And they use this embedding, and they found that, of course, GloVe is the best, right? But before I talk about that GloVe is the best, maybe I owe you guys what is name entity recognition, right? So name entity recognition is a very, very useful task. So for example, I have something like Chucky is flying on his broom, right? There's this task called NLP called name entity recognition, in which I can say that this guy is person. Okay, this guy is I'm not sure, artifact. Okay, I can name whatever the entity name, but I can define that this guy is a person and this guy is an artifact, and I want the model to learn to identify that whenever it's Chucky is person. How about flying? I don't care, so I don't tag it with any entity, right? So in name entity recognition, what is the input? The input is the word. What is the output? The output is the tag. You want the model to predict Chucky per is nothing, flying, nothing, on, nothing, kiss, nothing, broom, artifact. So you can feed all the and let make it as a training task. Of course, very closely related to name entity recognition is part of speech tagging, right? Or POS, right? In which what we want to do is the same thing but different thing. We want to say that this is a subject. This is a pronoun, right? I think I'm not good in English, but this is a pronoun. This is a verb. ING is called something. There's a word for ING. I don't remember. Right? Huh? Adverb. It's not adverb. It's something ING. Like, huh? Yeah, there's a term for anything with ING, right? Yeah. So that should be tagged like that. On is like preposition, right? His is like, there's another term. Bloom is like object, right? Huh? His is a pronoun. Okay. Okay, whatever. Okay. I'm bad in this kind of thing, but there's this task called part of speech tagging. And you want to input if Chucky is flying on his broom, the output is the part of speech of each of them, right? By the way, part of speech and name entity are already solved. You don't need to solve. Later on, I will teach you a software called SpaCy. Actually, there's already a video. Everything done. You don't need to do anything. It's all solved, right? So these are not something we want to do in your research or application. All right. Yep, last slide. There are three big limitations of Word2Vec. Local windows, we use statistics like below. Out of vocabulary, we can use character based like fast text. We did not learn that, but I introduced here quickly. It still doesn't understand context. We have something called ammo and actually bird. But by the way, you can see that GloVe does not solve out of vocabulary. GloVe does not solve context, right? You still have only one word for embedding. So yeah, we did introduce a SVD, and later on we introduced a GloVe that combine count and prediction base. And there are two types of evaluation. And I think we haven't talked about fast text, and we will talk about that very quickly. All right, thank you very much. I think it's exactly 10:30, and see you next Monday. Don't forget the assignments, okay? Thank you, bye-bye. Bye-bye, YouTubers.